Okay, I think we can start because they will arrive. So, Bin, after this very long introduction, it's an intense pleasure to welcome you, and the floor is yours.
Thank you. So thank you for including me in this workshop. It's meet a lot of new people, and it's such a nice, cozy environment. So feel free to interrupt me and ask questions. So my affiliations summarize pretty well. I'm a generalist. I do many different things, but I do work very closely with domain scientists like clinicians, and very glad to be here. So in case you haven't heard the word veridical, I didn't either. When a friend, Tian Zheng from Columbia, suggested it means truthful. It's a proper English word. It means so I try to interpret veridical in veridical data science in two ways. One is you seek truth in data conclusions, and we try to be truthful to the data science life cycle. So really see things as a system science. And data science is a foundation of AI because we use a lot of data, and it's not all AI, but it's very important. And data science life cycle is not just one step. It's a whole cycle. And often you go back and we make so many human judgment calls. Right, different people do the same problem or get different conclusions. Just want to point that every step of the way, we introduce uncertainty because of the human judgment call. They could be all reasonable, but we might have different conclusions. To really support my point, I've been on this for the last 15 years. 2023, 73 teams of social scientists work on the same data, raw data, and got very different conclusion for testing a hypothesis about whether immigration will induce positive or negative effect on social policy support. This is from different countries. They use the same data. They have the same social science hypothesis, but they got different results. So this is one source of uncertainty, and there's a similar paper from biologists. 100-some teams do the same data analysis, have different results. So this is now traditionally considered in probabilistic framework. And I did my own experiment. Actually, Zach helped me with this. We had the master's class last spring, and 18 students were willing to share the data. The first lab is cleaning this data from try to decide whether a child should be sent to CT scan for possible traumatic brain injury. And if you use the 18 different versions of data, you use the same classification method. We're not introducing this research degree freedom. You control that. If you've set a 77 and 99 sensitivity, and the 18 versions of the clean data will give false positive rate from 7% to 98%. They're master students. You can say they're not good, but they're master students. I don't know who else is cleaning the data. And so this really under-accounted for. To make things worse, these two Princeton computer scientists traced 48 papers with problems to 648 papers. So these false conclusions will propagate and just multiply. I jumped into this direction because actually 15 years ago, the reproducibility crisis and a lot of this famous study from Amgen and Bayer Healthcare have very low replication rate for landmark findings in preclinical oncology research, right? So that's why I started working on that. And now we have AI, right? There are a lot of false, like good things could happen, and there could also be a lot of downside, right? So this Science and Nature sounding the alarm, I think correctly. And then MIT has a report showing that in industry, 95 failure rate for AI projects because they need better data. But I'm saying that, yeah, better data will help, but that's not enough when you look at the whole pipeline. And very close to my home, Light Animal also doing data analysis. I wish they don't, but they do. So we have a project trying to help maybe to do better. There's also potential to help more people do data analysis more easily. So it's like the ups and downs. And California finally have a safety law last year, right? 2024, the safety law was vetoed, but the law is most about transparencies. And then Oxford has a report saying that, oh, these benchmark tests are not enough. they're just not enough to make sure it's going to work. So we have two elephants in the uncertainty: data cleaning choice, model choice. I try not to use researcher degree of freedom, because that seems to be very positive, because this choice can really lead to trouble. So it's the same thing. Some people call it research degree of freedom, but that's too positive for me, so I use the choices people make. Could be bad, could be good. And again, we need to think the whole thing as a cycle and many, many judgment calls. So for the rest of the talk, I'll go to what we build the veridical data science on through the three principles: predictability, computability. And veridical science for me is a bigger umbrella. And PCS is a particular way we're doing it. There will be other things coming into it. And now I'll show a couple case studies and the current projects and resources. So the three core principles are predictability. In the beginning, supervised learning. Now generalized to reality check, but I'm stuck with P. I can now call RCS. So it really means much broader for unsupervised learning. And the paper with my former student appeared 5-6 years ago. And computability, like in statistics, we have R, and then machine learning put computability very much at the center. Stability is a huge expansion of statistical sample-to-sample variability to every step of the way. And so it's a new paradigm. It's a unification, it's a synthesis, it's expansion. So you see familiar ideas, that's great, because I'm not saying everything's new, but this systematic coherence development, I think is very useful. I want to unify language and conceptual framework among ourselves and also communicate with stockholders and even managers. And trustworthy AI and AI safety need communication and interpretation. So when I started working on this 10, 15 years ago, I was in a fog. I was traditionally trained as a statistician. Now in hindsight, 15 years later, they're really common sense. Prediction check is about reality check. You can define it, but it's something we're often busy fitting models without worrying about it. Stability addresses new social uncertainty, and computability indispensable, especially at assignments. But also want to include, we have a paper on how to do data-inspired simulation, set some standards. And like digital twins, it's a particular way of doing data-inspired simulation. And it's really also taking statistics as a system science. Look at the whole process, not just probabilistic modeling. Compare with traditional framework, you'd see a statistics machine learning book. People often start with, there's a true model, and I think that's not a good framing, because you have to tell the student true model is actually not true. It's all approximations. And also make people think about assumptions. So not all models are created equally. And reality check is kind of in the old diagnosis, but we don't do it anymore. It's in some cross-validation, but it's not systematic done in statistics. And there are also different kinds of models, even you go for the probability framework. Some like Poisson distribution for emission of particles, we kind of take it as true model. That's good enough. But for PDEs, right, you have physics, it's kind of okay. But most of the time, the probability framework is imagined. We made it up. Why is a random sample? And we don't say what's the distribution, and we don't really understand the data selection process. So I want to really differentiate different kinds of probability models. That's another talk. Uncertainty quantification. It's a specific case of stability analysis. Stability that is a lot more flexible and easier to use than go to a quantitative uncertainty quantification. And documentation, documentation, documentation. There's no way out, right? I cannot say, sitting here, say, my method will work for you. You have to document your context. So do you see a Golden Gate Bridge there? Who sees a Golden Gate Bridge? Bridge. The bridge you can walk on. We actually don't know, right? So models are constructs, mental constructs. You have to build a bridge from the model to reality and back, right? And this is fog. Maybe it's there, maybe it's not. I don't know. But you have to see it with your own eyes instead of, imagine because you see the post, look at Golden Gate Bridge, therefore it's there. And we have a template you can borrow. And people say you care about stability and you do all these kind of perturbations and then you'll never go home, right? Because there's infinite possibilities. So you still have to make meta judgment calls and you document. At least transparency builds trust. Transparency also makes you think harder. When you write something out, you're more clear than, kind of work and I tried it. So it's both encourage the developers and the users. So I'm not moving away. But aggregation can really improve final results, right? So I'm not an experimentalist. You can also tighten the data collection. But I'm taking from the data collected and the cost under my control. And it's good and bad. We have a lot of freedom, but also combine good judgment call. Like different doctors, if I have a serious illness, you usually want to have two opinions, right? Second opinion. So that's the idea, and you combine. And record. This is related to what my colleague Gorman Lauken called forking. So they recognize there are many, many calls, but they didn't provide principles how to work this path. And with my student, it took us 9 years to write the book. Rebecca now is at Utah University, also a company called Arin. And there's a free version, English version, so you don't have to pay. And came out 2024 from MIT Press in the machine learning series, and hope you can use for teaching or just cover the whole data science life cycle. There's a chapter on data preparation, and people really like that because you don't see it in any other books. And then two people I think many of you probably know, Yuval and Yoel Benjamini wrote a very positive review for the book, and in the Harvard Data Science Review, and they summarized the review as pedagogical excellency, diverse examples, and projects. So we have all the codes and data on the internet. And the Chinese version came out last fall. And big thanks to 4 group members who actually used machine translation for the first version and edited my colleague Geng Zhi to proofread it. And 3,000 copies actually all sold out in 3 months because there was no free version. So the English copies are not sold out as well because there's a free version, I think. And Jack is here. We wrote a bridging paper from the 8-page 2020 paper to the 400 book and talk about generative AI. So that's a quick guideline instead of the original paper, a little high level, and the book very detailed. So where does this framework come from? I'm actually both a theorist and a practitioner. And I'm living at Sophia Call many years. I was a pure math major, and then theoretician, information theory, and I also live in the real life of cows. So I like to be a bridge. And this is just, you won't have time to read. A lot of the experience, wide-ranging experience in working with different domain problems went into building this framework. Just to show my credibility that it didn't come from nowhere by proving theorems. It's both the insight from theorems, mostly from the experience. And then we have developed many, many general methodologies in context of solving different problems. This is cancer research. And this is genomics, I'll talk more, and this is in computational biology about improving t-SNE and UMAP. I'm color coding them saying that this is general methodology, but they were developed in solving particular problems. I'll call in context, I try to make that very popular. In context research, and people have extended to other fields. So now I'm moving to the next one, which is case studies. So with this group, I hope some of the things we do will be useful for you too, because I developed general methodologies in context of solving a particular problem. So interpretability is critical for trustworthy healthcare. And PCS, I argue, is a prerequisite for interpretability. If you don't have reality-checked, stable models, I don't think you should waste your time to interpret. For development, it's a different thing. As a user, you just cannot trust the interpretation. Interpretation can be just a story. Could be real, could be a lie. And I'm going after causality through the PCS framework, right? If you look at, I see causality as a whole spectrum of evidence. I like the definition of philosopher Nancy Cartwright, who defined causality as you have enough evidence to act. And that's, you have physics laws like Hooke's law, right? You put the load at the end of the spring, you get bigger. longer, but sometimes breaks, so it's not 100% working either. And you have the statistical, we talk about clinical trials, right? It's a lot of causal inference. You still have to assume suitable. If it's all the enrollment and everything, you still want to make sure there's one version of the treatment and there's no interference to do the name and Ruby model. And predictability follows from causality. But when you add stability, we have stronger evidence for hypothesis generation for experiments or clinical trials. So stability is very related to the invariance principle in causal inference. People have tried to find the same factors driving some disease under different environment. The way I'm doing it include that, but also using pseudo environments related to different algorithms. If they come out to be the same, I trust it more. And then I don't claim causality, I call recommendations. And there was a lot of great talk by Mihail about GWAS, genomics. And I jumped into genomics about 10 years ago, interested in interactions, right? Life, these are two quotes. In nature, nothing exists alone. This is from a French mathematician. They aim at assigning all things themselves as the dogmaticists in their simplicity imagine, but the relation between things. So it's really about interactions. I want to go beyond GWAS and marginal importance to interaction. So we started with Drosophila. They are very nice and easy to breed and all of that. So this is the first paper we put add stability. The P is there, random forest. My collaborator, Ben, already told me, and Basu, now Cornell, professor there, Kambir, is with a startup with a colleague here in Berkeley. So we added stability, a property, to random forests. We want predictive and stable higher level interactions. And with the data we have in enhancer static prediction, we found 20 pairwise interactions, and the existing literature validate 80% of it because there was so much work in Drosophila, right? Drosophila, we are 65% shared in genes. And we are doing pattern discovery. Pattern recognition, you know the cat, you look for it. Pattern is that we don't know what the pattern we wanted. So it's a lot of search, and it's very expensive. And we know from Drosophila there are false order interactions. It's not just important genes, additive, and there's also something called the French flag model, saying that biomolecules have to have abundance for them to interact. This points to a different mathematical interaction than Fisher worried about, which is decision trees. You want things to threshold high to interact. Polynomial might exist, but it's not enough. And Fisher didn't have this information, right, 100 years ago when he posted his epistasis work. So that's why, and random forest work very well prediction in genomics already. So everybody knows about random forest? Decision tree, okay. So what we did, so people already said that you have random forest, that means you have a forest of trees. People already had that idea that if two genes fell on the same path, they might interact. But nothing was stable, so they couldn't interpret. So we know that we need to add stability. And the way we add stability is that if you take random forest, the output includes something called importance measures, MDI. So the iterative random forest, the second iteration, we just upsample and downsample based on this importance instead of uniform sample. That's the original random forest. And we iterate. And then we collect. This is where you use some CS, random intersection trees, to collect the shared path. And we have after loop of stability, and we get a stability score. And the same cost as random forest. So the Drosophila enhancer prediction problem, each unit is like a segment on the DNA. You measure transcription factors and things like that. And then you can see that this is on test set. The predictive accuracy more or less stay the same when you do the iteration because we added the regularity needed. And here is the stability score. We just cut it at 0.5, seems reasonable. And these are the names. This is 3 transcription factors. This is 2. If you know Drosophila, this is the hunchback, this is cripple, right? This is known genes. And we found 20. And then we look at the literature, 80% were already proven to be real. We didn't do experiment for that. And then we spent more time to make it signed. Because in the beginning, just two genes on the same path, we see the interact. The sign means if the decision tree is larger, that means positive, and less is more precise. So we work, it's an archive paper, and put it in the UC Santa Cruz Genome Browser track, so people can use it to help them to do developments. Then, 2018, we got this award from Changzhoukou Biohub. They forced 3 campuses to work together. So Yuan, cardiologist, still Stanford. He was at Stanford now at the company, and Ben, my collaborator, and people from UCSF. I want to point out that the 2 young people, Qingru Wang and Tiffany Tan, she's returned to China as an associate professor, and she's a professor at Notre Dame now, assistant professor. So it's a huge team. And we actually wrote the proposal about a heart disease. Couldn't find any signal from UK Biobank data. We tried another heart disease. We couldn't find any signal. So this is the last one. We did find some signal, which is actually Yuan's specialty. It's hypertrophic cardiomyopathy. I think the name was already mentioned in last talk. And if you have this condition, your heart, left ventricle heart become enlarged, and you have a lot of problem pumping. It's 1 in 500 people. It's not quite rare random, but it's kind of common rare, but not very common. And prior work showed there's a genetic component to it. And also cell size is something we can look at. We used a label from UK Biobank. We couldn't beat random toss. In hindsight, a lot of people have the problem, were not diagnosed. So we had to go by use deep learning to find the volume. Use other people's algorithm, deep learning algorithm, to find the volume, and we properly normalize it. And that become our new phenotype. And then we have the problem satisfying P to know whether maybe we're just fitting noise. So we binarize it and say that if it cannot beat random toss, we have no signal, we should just go home. So we binarized. And I think the pipeline we call low surf as a recommendation system could be useful for cancer phenotypes, maybe autism, ADHD, the people here, right? It's really, we developed general methodology and tested in this case, but the methodology should be useful for other. So the pipeline really shows we reformulated many times, right? We binarize it so we can satisfy P. And this is a machine learning algorithm for prioritization. If you do P-value, nothing going to pass P-value. But the order of genes are still useful interactions. And after we submitted the paper, the referees really said, you have to compare with traditional interaction models. We did and convinced them based on annotated database. So that was not done. It was after the gene silencing experiment. I thought we had the gene silencing experiment, the case made, and we did tons and tons of other analysis to make up the case. Yes?
So for the interaction, did you look at protein-protein interaction?
Right now, in the beginning, this...
Or co-expression?
So right now, we have a project using protein large language models.
PPI?
Yeah. So this one, we checked with protein-protein databases and believe the 2 epistasis interact we find are not protein-protein interaction. It's more like indirect regulation. We did compare, but we didn't take into protein information for this work.
Okay, yeah.
Yeah. The ongoing work does. So here's the pipeline, low surf. Low means low signal, surf is assigned iterative random forest. So we do have to use GWAS. And to introduce stability, we use 2 different GWAS, BOT and Planck. And we took the top 1,000, that's the judgment call, and we took a union because we don't want to follow any too closely. And then we binarize the new continuous phenotype, and we did stability analysis. We did 20%, 15%, 25%, get similar results. And then we fitted on this SNP data. But when we interpret it, when we see a split on a SNP, we mapped it to a gene. So when collected the interaction, we only look at the gene level because SNP is too unstable. So that's what we did. And then we find all these genes, Titan, right? Michal had that in her talk, and growth factor. And then CCDC141 is actually a gene very close to Titan. But we see that they're not always work together. They have different functionalities. And then we find also 3 epistasis possible targets. So to summarize the pipeline, we used unrelated individuals, so we did random split. And then we used binarization, and we tried all other methods, right? I have been promoting that you use multiple methods. They all give very similar 55%. It's pretty low. I've never done a prediction problem before this with 50% classification accuracy. But then we interpreted, use the SURF, signed iter-random forest, for multiple reasons. It's consistency at the top, also because this French flag model, right? You have this interaction, you have an interpretation. And then we did stability check, and we did the parallelization for wet lab experiments. And one thing I learned from the Drosophila project is that you don't go to your experts to say, here's what I got, what do you think? I did that time, but now we try to fool them a bit. We give them 3 lists, top ranked, middle rank, and random, to fight back a bit confirmation bias. And my collaborator all passed it so far. This is, I think it's more authentic getting information than they just like you and they say, yeah, it makes sense. And then we did a lot of annotated data. I even did a little bit to see this. There's no annotated data about interaction, so this is all single gene, and they seem to be reasonable. And we cut off here. We only took the top 3 genes. We didn't go to the next. And then this was done after the experiment was done for paper publication. These 2 ones, the referee pointed out 2. One is called pairwise regression. The other is called MAPIT. It's all linear model-based, some random effects. You can see that the interaction they find are not backed up by annotated database. So we passed the referees. And then experiments. So Chen Ru and the undergraduate student who provide the sample, Nate, did gene silencing experiment. It's cheaper. So you have these kind of stem cells. They don't look like allocated muscle genes, so you can just look at the diameter. And she designed this single cell size measurement. You just push the cells, and then you automatically find them. You calculate the area, and you find the diameter. So we did 5 sets experiment. And we also got 80%, I think, by the same as last time. But it means we have high success rate. And the 2 epistasis interactions could be possible drug targets, I'm hoping. And the paper is like 88 pages. And the first response to the referee was 38 pages. Right? So this is a shout out to my main collaborators. OK. Actually, before we did that, just mention that we have another paper. We tried a simple human phenotype, red hair, as a proof of concept before we went to heart disease. And we have something called epistatic, or we also based on the tree. We use random forest, and we do stabilized or robustified p-values. So we get bigger p-values. And it was published and was led by Merle, who is now professor back at Regensburg, Germany, and Carl I mentioned, and James, who is now a company with cardiovascular drugs. And then we also did some theory, since we have TCS in the title. What we did is that we have a linear combination Boolean interaction model as a regression function. We devised a theoretical version of the iter-random forest because we couldn't analyze it. It was too many randomness. And we showed that for this model with independent features, we can actually find these interactions. So this is a bit theoretical to back it up, what we did. Another one, I'll be very, very brief. This is the other one took like 7-8 years. This one was like very straightforward from PCS. So I mentioned just say you can actually apply very easily, very effective. So I start connecting with Hutchinson Cancer Center and Zhijing Feng, who really think this will be used for cancer detection, and brought me into the community. So I did a study with MD Anderson for pancreatic cancer. They just embraced it, and we did it the way, and we had a very nice paper with editorial comments. But then I wanted another example. I was giving a talk at the EDRN, which is an NIH Early Cancer Detection Network, and I want to go in with more example than one. So at the time, Aru Chanayan is a PI in EDRN in Michigan. They already had a paper. As you may know PSA is the standard test, but has very high false rate. 90% sensitivity, you get 90% false positive. So their paper with 18 genes already lowered by 30%. It's still not great, but it's much better than 90%. And they have a startup. So that's week 1 in. We said, can we redo the analysis as a stress testing? And we went in with Tiffany and Anna, now UC Irvine. And we have a paper now called Simplified. So we did redo their cleaning, talking to the person, and they did it very well. You change things only by 1% to 2%, because one person doing it is like 800 data points, so it's small data. And then we went further. We said they use elastic net logistic regression. I don't think there's any research show that's the true model, right? So we said we introduced 8 other good methods. And then we did p-screening. We ended up with 6. And then we did stable ranking. So each of the 6 methods has important measures. So you can rank the genes according to that. And we took average. Yes?
For the 8 genes, so for the 18, do you see interaction or you see?
No, this is all single ones. We didn't go for interaction.
Okay, so it's added.
Yeah. We could have done the RF, but we didn't for some reason because they did the linear method. We did use random forest, but we didn't go for the interaction.
Okay.
In theory, we could, but I have to go back why we didn't. So we didn't. Good point. We did just the important genes, single important genes. But the data is only like 800 data points, so maybe, but we didn't. So we're able to bypass the combinatorial search to find the top ranked gene, second and third and fourth. When we hit 8, we get similar results. And we also have external validation from Hutchinson, and we filed a joint patent. And his startup, Linux Stacks, has the exclusive right to develop into, they have to do more work. If we get lucky, they get approved, and the cost saving will be like close to $1 billion because we cut down the false positive. But obviously, as some of you might know, it's very painful and it's very costly, about $2,500 per test in the US. So this is very straightforward. This is not hard at all. The first one was many, many reformulations. Okay, so the last ongoing project, I have Nicole here, and I don't know where's Aaron's here, so 2 of my people who really work. So this is ongoing, and I really appreciate physicians to give us feedback, is we call, how can we safeguard users of AI? So AI continues to experience fragility and instability, but we have met rapid mass deployment. We know hallucination issues, inconsistent reasoning, sensitive prompt phrasing, but there's no real user guide how to use AI, right? If you buy a bottle of medicine, usually there's some label saying pregnant woman shouldn't take it or something, right? But there's nothing. It's just all rolled out for the general public. And historically, we also deployed very powerful technologies before learning how to use them safely. Automobiles were deployed before we have accidents. Antibiotics also were deployed before a lot of safeguarding were in place. Internet just organically grow. But now I think we're in a very unprecedented situation because the speed of the technology is happening so fast, much faster than any of the early technologies. So if we're not proactive, I think the disaster probably will be even bigger because the reaction time. And there is effort with the safety law of California, right? EU had many laws, and there's NIST in the US also have some framework, and there's an institute, we actually got a grant, AI Security Institute, AC, and we have industry reports and teaming research efforts. So this is taken from my colleague at iSchool, Deirdre Mulligan's talk from last week. She organized things into these different imaginaries. So this is her terminology. The first she called frontier AI. Basically, that's dominated in the big tech companies. And then responsible AI, like hospitals, organizations, pragmatic in the legal government, right? So this, it's basically different community of people interact and have different emphasis on the AI safety, right? This is my law and compliance. There is fairness, transparency. There is benchmarking and scaling and red teaming. So they do kind of related things, but they're not the same. And evaluation shapes governance, but we have a gap. AI governance relies on existing technical evaluation practice, benchmarks, as I said, red teaming, safety cases or hallucination, you do adversary attacks. But it usually comes from the big tech companies, and they want the very big risks, which need to be taken care of. But as a user, like I use it a lot for medical questions, we don't have any really systematic evaluation or measurement. That's the gap we try to fill. And there's no incentivification either about why we should care about this user point of view, but we want to make it a real field we call green seeding. So this is just, if generative AI is a scooter, this is all Gemini generated. You can see the parents are a bit worried, right? I don't have young kids now, but if I'm a parent with teenagers, I'm worried about they use too much. They're not learning writing, and they're not learning the rhythmic, right? So they're worried. So my inspiration was a photo of a friend's grandson with padding, right? And see, hopefully the parents wouldn't worry, right? And that's the idea, is can we put some padding around this scooter, which is generative AI. So here we have Nico here and Aaron here, so they will answer the hard questions and the details. And then Hao is also a student in my group, and Rujing is from University, and there's a major collaborative emergency doctor from UCSF, and there are many people engaged. You can see it's a collaboration between Berkeley, UCSF, and New York, Melbourne, and then UIUC. So it's a big team. So the paper, I think we might have put it on my website. We're not ready to put in archive yet, but if you want it, I can send you the link. Just shoot me an email, beamy@berkeley.edu. So it's a user-centric program to our trustworthy AI. We define green seeding as a research program to study generative AI behavior and the benign deployment realistic user input. Variation, aim at producing empirically validated evidence-based guidance for users. Right, so we want to have representative tasks, task-aligned evaluation metrics, realistic perturbations, and all that intersects with all the three imaginaries: frontier AI, complement red teaming, responsive AI, guideline grounding in systematic validated studies, pragmatic AI provide deployment relevant evidence. So this is massive use of AI. So red teaming, green seeding, you can compare that. Red teaming is how can adversely break the model? We are asking how should people use this system to their benefits, not try to break it, just for their own benefits. We usually have benign real-world inputs, not adverse inputs. And we don't have external extreme failure modes, but user variations. And validation-driven, not the edge case-driven. And we want to user-centric evaluation. Both are necessary and complement each other. And we want to see how to take advantage. I'm hoping if we make a good case, people in education will find this interesting so that they can start discussing how the teachers can help their kids to use it for their benefits and deprive their normal development. So this concept, I believe, very useful. And the case study is ongoing. We're in the middle, and all input, especially from physicians, will be well welcome. We tried to do a case study with ER doctors like Aaron and his colleagues at UCSF. And we want to look at open-ended questions. That's more realistic, not medical exams. Those actually introduce a lot of misalignment because then the large animal model don't want to give kind of ambiguous answer because they want yes or no. So we want to look at more realistic, and we used some pilot study of this medical exam data set to find out what are the sensitive dimensions of the user input the large language model react to. We find that one thing is about the tone, right? If you're very anxious or something, they have this psycho-offensive behavior, might try to calm you down, and so that's what the dimension we decide to poke. And we hope, this is our hypothesis, we're not there yet, is that certain prompt semantics might lead to more reliable and less sensitive diagnosis outputs. And if it's the case, then the organization, suppose some hospital have a user interface, and they take the responsibility for the user to go to their website to use the large language model instead of just ChatGPT. And they can take the input of a user and do some converting or neutralization, so give them more authentic, more reliable answer. So that's where we went in, or the hope, right? I think the general conceptual framework, I'm very confident it's useful, but we have to show a useful case. Yeah. And the concept of multi-is that we can use user guidance. There was a columnist from New York Times or Washington Post already writing a column saying that I talked to my friends, and it seems like if you ask questions this way, it's more reliable. So people already try to go there to give advice on how to interact with large language model related to medical questions. And we can maybe do automatic prompt conversion for better deployment. That's our hypothesis. Yes?
Sorry. So, automated prompt I feel like there's a risk that I want to get your take on with something like automated prompt conversion, in the sense that the user's intent out of engaging with an LLM can change, and that can potentially be used not for these noble intentions, but for sort of other intentions in the context of sort of organizational use. So are you envisioning a system where like the automated prompt conversion is really the user is using a tool, and then sort of under the hood their input is being changed? Or
for example, I like to ask a user for the permission that.
Okay, yeah. Great.
So they are transparent.
Yeah.
Or we just give them to themselves and they do it themselves.
Okay,
definitely, that's a very concern. You don't want to kind of secretly change things. Yeah, so it should be transparent. Maybe you can ask, do you want to use this like a connector to make things more reliable?
Yeah.
And they can go back. So transparency, exactly. And the study designs that we actually took something called healthcare magic data sets about real interaction between patients, queries, and doctors, and took that and made it more structured. It's open-ended, but we use something called SOAP from the medical training, try to organize the information into a more structured format. And then we already identified some influential variant prompting factors like tone, and we did a very simple neutralizer to change the tone. We haven't really explored like chain of thoughts, all of that. And then we compare with the original, to the original answer to the original prompts. And we're in the middle of getting a more, we had input from physicians, but we're not there yet. We had the 3 AI frontier large language models as the judge, but I want to evaluate the judge, so we're in the middle of doing that. And just this is a quick run that the principles, since I'm giving a PCS talk, it's very much guidelines in all my group projects when they're applicable, almost all of them. And we really think about the reality check, how to make more realistic like data set. We took the healthcare magic data set and curated and changed the structure, make it a data set we call DX that other people can use as well. And we relied on large language models to automate the generation of what are the possible answers for diagnosis, because it shouldn't be just unique, because there are many possibilities, and we try to evaluate that reference generation with doctors. And we want track to experiment because we are very financially constrained with how much time we have on these different platforms. And we try to be efficient. And so if all the large language models agree, we tend to have fewer samples, do important sampling and sequential testing. And we have stability, multiple frontier models, and multiple data sources. So it's all this consideration, trying to put it together to have something which is more trustworthy. Preliminary result is that we can change things. But the question is that for better? we do reduce the range. And if you look at the doctor's responses, they tend to be not as wide-ranging. So the question is that making things better? So the good part is that we can change things, but this is a very simple neutralizer. Just you take the tone, make it very kind of blunt, and we basically reduce the possible diagnosis. You can see for different users, for people who want certainty, they probably like it. Instead, they get overwhelmed, right? But other people, they might want to see all possibilities. So we should allow people to switch, right? Maybe they stay with the original prompting, or you want fewer possibilities. And there's trade-off, right? The doctor also told us, so we work very closely with Aaron. They said there's something called cannot miss diagnosis. But then the real doctors also missed. So we do better, but they also miss. So this is the question I think more doctors have to engage to see what's a sensible metric and for what type of patients. In terms of heterogeneity, it shouldn't be for all patients, but some patients might like it. So takeaway is that we can reframe our study for everyday use, complementing red teaming, user-facing behavior, and trade-offs measurable. And the green sheeting needs domain-specific realistic data sets, so you need to really interact with physicians so you can really realistically measure deployment behavior. And we show that very simple neutralizer can change diagnosis behavior of large animal models. But we need to see, is it higher quality? But that's why it's ongoing. So looking ahead, does stability improve quality? Maybe for some patients it does. But others, maybe not. They want to see the whole range. And whether richer prompting strategies can give us more freedom to change things, maybe to have both higher quality, like in terms of more on target and smaller range. That's what we want. But we're not there yet. Yes?
Just very quickly, how do these conclusions remain stable or change if the LLM versions are changed?
So you have to continue to do this. Yeah. That's one problem. Yeah. You really need a continuous evaluation, continuous monitoring. Because I don't think they can guarantee that some desirable property last version will be kept. Remember when ChatGPT rolled out, a lot of people got unhappy because they could not talk to them as friendly. They had to bring it back, right? For some people, that desirable property disappeared in the newer version.
But there may be some elements like neutralization, which could be relatively stable across different versions.
We hope so.
Pieces like that, which one could build on.
Yeah, so that's something. If the labs are open, they can, before they roll it out, they can do some checking. But we don't know what are the things they check. So I have another paper saying that they should be open for user supplied case studies so that it's not just what they decide. Everybody has blind spots, right, including them. I know talking to some people in Gemini or work on it, they couldn't match all metrics. They did choose for the next version. Because it's impossible, right? The foundation model is very, very ambitious. So that's why at the organization level or the responsible AI lab, that institution can do more. But they should also collaborate. So the current direction, we did other works. So this is work if you guys like single cell. We also use PCS to improve on t-SNE and UMAP because it can be so unstable, especially targeting smooth data structure you see in disease progression, normal development. So that's something just came back for revision from patents with my collaborator Roma from Harvard Biostat. We also have a whole, starting from the book, pipeline for uncertainty quantification for prediction and for deep learning. So really improve over the conformal approach, the standard ones. And we use 17 data sets, also look at subgroups. We definitely have very good performance. And the follow-up, Jacob is here, combine conformal quantile regression with PCS UQ, and we got further improvement. And then the same idea of hypothesis generation, we also work with now my colleague, Alec Huth, to come up with hypothesis generation, which are paragraphs. And then we feed back to fMRI experiments to show that this voxel cares about this, say, food or things like that. So it's the same idea, right? We come up with hypothesis here is this voxel cares about this type of concept of semantics. So we did the experiments, and we revised it for Nature Neuroscience. And RJ is a postdoc at Columbia, and Chen was my former student at Microsoft Research. And this is a paper now 2 years ago, tried to say what we wish, with my colleague here, the big lab would do in terms of benchmarking and evaluation. And we have software to help you to do stability analysis faster. And we also have this like simulation guides, I think relevant to digital twins, we call merits. It's like you want modular, it's follow the PCS framework, it's like a C part of PCS. This is our package to make multiple simulations very easy, because for simulation, you shouldn't simulate based on one model. You should do multiple models. And for theory, I think we should analyze something under multiple generative models too. So, and the model should capture some reality. And this is the merits, right? My student Corinne led called Modular, Efficient, Realistic, Intuitive, Transparent, Stable. The kids are really good with names. Yeah, who doesn't want merits? But so they're good branding. And we have a documentation, a template you can borrow and change, especially for beginners, that help to streamline. In my class, they all have to write documentations. It's some revision of this form. And the flow with Zach here. And we're running a workshop in Paris this May. So if you're in Europe, not too far, watch out on my website. And we even have a date. We did one 2024 with Stanford at Berkeley. And we did another one in Rome. We have good places. And we went back to Berkeley, and we're going to Paris next year. I hope we'll do it in Stanford. So it's right before the French Statistical Society meeting. So we try to pack that date. And the book, try to use it. It's free. And you have your Benjamini's positive review. And here's something from a former student of mine who is doing a startup covered by Fortune. They use PCS. And also I have some testimonial from a friend, Jessica, who is the head of AI from Bridgewater, who is a big hedge fund. Also they use PCS. So on that, to summary, versus data science, reality check, and documentation and stability analysis. You need PCS for interpretability, and we want to do hypothesis generation. And we have all these different things that, especially the low surf and PCS ranking, is just a method you can use for your problems. If anybody interested, we have codes on our website. And next, if you use t-SNE and UMAP, I think it's an improvement. I found uncertainty quantification. Okay, papers. Thank you.
Thank you so much, Bin. Yeah, and thank you for your mail. Yeah, so I mean, I think we can share some of the data. So I don't know. Ethan, can you do something to share the? This is you, Ethan. for me, you're the new Ethan. That's why I'm.
Okay.
And we will see how we can share the PowerPoint or the information, because that's it's a lot of information. So are there questions? Yes.
So first off, do I need people online?
Probably.
So first off, thank you for the fantastic talk.
Thank you.
I think that's something that's often assumed in questions of reproducibility or veridicalness. I don't know. Yeah, but is there's the piece before even the PCS framework comes in terms of what claims are you communicating that you're making, that you're saying are truthful or valid. And I think in science we at times intentionally or otherwise abuse the ambiguity we can leverage in that because it scales between the sort of impact we can claim and the challenge of actually stating something or establishing something in a truthful way. So I wonder if you can comment on how the piece of, what claims are we actually making and can back up versus what claims are sort of being implicitly communicated. How does that sort of relate to the PCS framework, or what are your thoughts? Yeah, if that makes sense.
Yeah, I think I will put it into a bucket of like a problem formulation. Right? As the HCM, the heart disease case study, we reformulate the problem like 4 times, right? But for me, it's the experiments that made the case, right? Because we could be fishing around, right? But the experiment completely external. It's nothing to do with the data analysis except this recommendation. So that's why we submitted. I thought that was just the strongest evidence. But if you don't have that, then you just say it's a prioritization, and just said you should report you tried other things as well, right? So I think transparency will help. It still might be valuable, but I think it won't be as strong without the experimental validation. That's my critique of the observation study, causal inference in general, that people tend to claim causality too fast, right? There are a lot of assumptions, and there's no follow-up, and some people write a little more, other people just. So you basically put in the randomization through the propensity score. And for me, that's a huge worry. And we are just saying, we're a recommendation. You need external validation. So we don't claim causality. I said towards causality. And that separate the different kinds of evidence. I think transparency will help. It won't solve all the problems. You still might overshoot and all of that. But without transparency, you definitely do it much more. Yeah, so documentation.
Thank you for this really rich talk. And going back to the first part, you mentioned in one of those case studies, I think I happened to see that some of the ranked genes were microRNA that you didn't mention, but it was so fast, so I think in the TTT, a little bit earlier.
This one?
Yeah.
This one?
When you, exactly. When you showed the list, or even there was the list in which microRNA were there, even the previous list.
This
it's in the,
This too?
No, those are not microRNA. I thought there was another slide, maybe previous one, that showed a few, and I was wondering, for sure I didn't make it up. Maybe it's there somewhere.
Maybe this is, let's see.
Yeah.
This is from other people's methods.
Yeah, okay.
Okay. So we didn't try to say that other methods don't work. We tried to say that this is a good alternative method, not the mainstream. Yeah. So this is from other people's methods.
Okay.
We didn't really dig too much into it. Yeah.
It was earlier. But anyway, I just thought that if it was there, and we can look at it later, I think it's a very interesting and often overlooked type of regulation that you asked about protein-protein interaction, whether it's really physically touching. Or, I think a very nice kind of hook are exactly those messenger microRNA that are working directly with the RNA to potentiate the expression of the gene. So somehow people are looking naively at protein-protein, ignoring this super important layer. So I think... both of them, through our digging around, we don't think they are protein-protein interaction. Yeah.
And then it's more like a locus, because you said it was about the same locus in the compound.
These two are very close.
So it's maybe like a regulation.
Yeah.
So that's my point, that the regulation could be really in a different direction.
Yeah, so I will share with the follow-up work. Yeah. We basically compare with the GRID database and the other called string. Right, so we see that our methods find non-physical interaction genes.
String ignore microRNA and other layers. So
so if you have a better database, that's ongoing. So if you have other database we can compare with, that'll be great. Wonderful. Yeah.
So this is perhaps a bit of a philosophical question, and just to give you the context, so I'm a computer scientist, and I was listening to your talk. And this was an exceptional computer science talk, if I may say so. I mean, you talked about things like documentation, which are very, very important, very basic things in software engineering and so on.
You say it's not a computer science talk?
No, it is. It would have been an excellent computer science talk, if I may say so.
So fits TCS.
So the question is that when you sort of see this increasing sort of convergence of statistics and computer science, and by the way, a version of this question was once asked from Kolmogorov when I was there, and I heard that. And Peter Bickel was asked this question, I heard that, so I wanted to ask the question from you.
Okay.
Which is, how do you see the future of statistics and computer science?
I think we have more and more overlap. And I'm also part of computer science, right? That's why I want to become a faculty. I'm in Berkeley, we have this 0%, means I have the full rights, but I don't teach. So I don't worry too much myself. I'm so whatever interests me, I go in. The field's boundaries, I don't see it. And I say I'm a statistician, machine learner, data science, whatever makes you happy, call me that. So that's kind of my attitude. I'll leave those questions to the administrators.
So the boundaries will dissolve at some point in this conference?
Yeah, we have to organize ourselves to evaluate some way. Let's do that. But for example, I was at Bell Lab for 2 years, right? We always cross boundaries, right? They like that. But you still need the manager to evaluate you, but you might get some input. That's not a hard problem to solve. As long as we solve problems, I don't care too much what we're called. And I think that's for my chancellor to worry about. And I don't worry about that. The important thing is, but for students do have we have this question, we have statistics major, data science major, there's a little question for advising. But for me, I just felt like I would say that data science is a little more CS maybe than statistics, but actually I think data science is the modern applied statistics. But there's also a common perception that students, we need to differentiate a little bit at the student level for them to choose majors, I think. But they can just look at the courses. They should also find greater information than just a name. So I encourage people to really look at the curriculum. For evaluation, I think it's not a hard problem.
Yeah, it reminds me when Bob Dylan gets the Nobel Prize for literature, and he was asking, is it really literature? I don't care so much.
Also
so it's, so and I think
names
Shakespeare never thought about, is it literature?
I mean, my role model, my hero is Da Vinci, right? That's the ultimate, a polymath. That's what I think we should all go back there a bit. We got too specialized.
So I can say that your answer is much kinder to computer science than Kolmogorov's answer was, and I can tell you offline what
Oh, because I'm part of computer science, maybe he wasn't.
Yeah. Other questions about statistics, literature, epistasis?
Bob Dylan,
Yeah, Bob Dylan.
Krumgraf.
Yeah.
All great names.
Okay, so thank you again, because I have millions of questions. We can, yeah.
Thank you.
So I think there is a lunch then this afternoon. Yeah, make it 1.